Plunger lift optimization, a case study of monitoring plunger dynamics with non-intrusive acoustic tracking, Mr. Muhammad Hassan Chaudhary. Mr. Hassan Chaudhary is Deputy Manager, Production Engineering at United Energy Pakistan Subsurface Division. He has more than 5 years of versatile experience in E&P industry, including the services sector. His proficiency spans domains such as production optimization, well performance, well integrity, well stimulation, rigless operations, planning and implementation, and evaluation of new technologies. His academic background includes a gold medal from NED University of Engineering and Technology in Petroleum Engineering. Please start.
So this is Hassan Chaudhary. There has been a recent change, so I'm currently working as a Deputy Manager in Commercial Department at United Energy Pakistan, UAP. At the time of writing this paper, I was part of the Production Engineering and Technology team, where I was directly involved in the acquisition, trials and implementation of this technology. So my paper is on plunger lift optimization, and is focused on some case studies that utilize the non-intrusive acoustic service to track and monitor plunger dynamics. So I'll be starting with the agenda of this presentation. I'll be starting with a brief discussion on basics of plunger lift optimization. Plunger lift operation, followed by a brief overview of the acoustic survey equipment, the working principles of plunger tracking and its value addition, and how depth correlation and interpretation is carried out. And lastly, the case studies, results, and some operational recommendations from our end. Just a brief overview of how plunger lifts actually work. So these systems utilize the reservoir's own energy to lift liquids from loaded up wells to surface, and thus that makes them a very cost-effective solution because there is no external energy in the loop. So a piston-like plunger reciprocates up and down the valve that lifts liquid to the surface. That reduces the flowing bottom hole pressure, increases the lift, and it allows a sustainable flow from the well. The plunger cycle consists of majorly two phases: a shut-in phase where the well is shut in at surface, and the bottom hole pressure and well pressure is allowed to build up. During this, the plunger falls to the bottom and rests on the bumper spring assembly. This is followed by a flowing phase where a pressure differential is basically created across the plunger that provides it the energy to lift the weight of the plunger itself and the liquid that has been accumulated over it, it lifts to the surface. This is primarily known as the unloading period, and it's part of the two processes that are occurring in the flowing phase. So the other being if you can see on the part on the bottom right of the screen. So the other being the afterflow period. So the afterflow period is basically when your plunger has reached back up to the surface and is caught at the lubricator, and the well continues to flow gas into the system at or above critical velocities. So these cycles are automated by motor valves that are controlled by electronic panels, and these electronic panels have preset timing configurations that define the start and end of each period, the shut-in period, the unloading period, the afterflow period, to simply put it. So these cycles repeat throughout the day to ensure the liquid removal is consistent, to maximize production from the well. We have fundamentally two types of, we can categorize the types of plunger in broad two categories. A slow moving solid type plunger, and there are some fast moving continuous or bypass type plungers. So bypass type plungers have a few ports that run through the entire length of the plunger, and these ports allow the gas to escape through them when the plunger is falling. This allows the plunger to fall much faster than the solid type plungers. Right. So, having established that context, now the plunger lifts require frequent adjustments, particularly in the time parameters. Due to the varying reservoir conditions that arise due to changing well dynamics, because the liquid loaded well is now unloading liquid. These changes may include varying GLR, the gas lift ratios, declining bottom pressures, or some performance issues as well. For example, incomplete plunger travel or overcycling or liquid fallback. So now, the traditional methods, they utilize mostly guesswork to estimations to counter all these issues. But the truth is that all these issues are difficult to detect without the presence of a dynamic monitoring tool and just with guesswork. So this is where plunger tracking comes into the picture, which is obviously non-intrusive, which is the main benefit of it. And just for context, these wells are very marginal, and costly well intervention is not always an option. So even when it is an option, you don't have very much options for well intervention, because if you imagine there's a foreign object which is the plunger cycling up and down the well, we don't want it to stop. The cycles throughout the day. Right. So this slide is to establish a sense of familiarity with the equipment and how the acoustic survey technology works, which we are using basically for plunger tracking as well. So foremost we have portable computer, which we call the well analyzer, a couple of cables going out to the gas gun. The gas gun itself is an assembly of a couple of valves, a high pressure volume chamber, a very sensitive pressure transducer, and equally sensitive microphone. So in usual operation, what happens is that you mount the gas gun on the welder, and you charge the gas chamber with nitrogen at a differential pressure to welder pressure or casing pressure, and then you abruptly release the pressure into the bore. That creates an acoustic pulse that travels down the bore, and it reflects or echoes upon encountering any restriction in the bore or ultimately the fluid level. So these reflections are recorded at the surface through the gun microphone, and they're recorded against strip time. The strip time is then correlated with depth, and when you have the depth of the liquid level, we can approximate with quite accuracy the bottom hole pressures at the well also. So we actually presented a paper on this in ATC 23 last year. So the same equipment is being used for plunger tracking as well. The working principle here is even more so simpler. Again, the gas gun is nippled upon the welder, but this time it is only meant to hear the plunger fall down the tubing. No shots are fired here, right? So this is known as passive acquisition, and the data that is being recorded is the welder pressure and acoustic noise. That's it. It's recorded, processed and synchronized against time, and that's the only thing that's required of the welder. Operational parts done. The data comes to office to us, and what we do is we adjust the acoustic trace on depth scale. Also, to simply put it, we correlate it with the tele depth, and we will come to that in the later slide. We'll discuss in detail. Well, once that's done, what we do is we skim through the trace to identify some key events that identify this beginning and the end of the plunger cycle periods that we previously talked about. And we will also discuss it in the next slide. Once that's done, we are able to generate a simulation of the entire plunger cycle. So I attached a snippet of it there, but it's a video. For some reason, it's not me. Regardless, this is followed by interpretation, where the interpreter analyzes lift performance and identifies potential areas which may have room for optimization. And then, it's always good to have a base trace of each plunger lift valve, so you know what's actually happening in the cycle. So the value that it adds for production engineering is foremost, it's non-intrusive, it's easy, minimal risk, it has little to no cost, very meager cost, mostly just human resource, there are no consumables involved. This helps in cutting down the cost of surveillance, particularly in this context where the wells are very marginal. Above all, the guesswork that is involved with the traditional methods, it eliminates or at least reduces it a lot. So we may have on either sides some limitations. One of those are signal attenuation in deep wells. Plunger lifts are not installed, not deployed in very deep wells, but if you happen to track a plunger in one of those wells, the signals, the acoustic signals would be a bit weak, and identification of the key events would be a challenge. So next is interpretation itself, because there is a learning curve to it, but there is a lot of literature available and some on-demand trainings as well to overcome this issue. Lastly, if the acquisition environment is noisy, so for example, there's a compressor or a pump running in the background in the well, or there's a remote nearby. So that would result in some noisy data acquisition that will make interpretation also a bit difficult for us. So diving into more details, comes the point that how do we correlate the required well pressure and acoustic data with depth. Right, so what happens is that when the plunger is falling past a tubing collar, it generates an acoustic pulse that travels through the gas of the tubing to the wellhead, and the microphone in the gun that I talked of, the sensitive microphone in the gun, it detects it and it records it. So we count the number of these pulses, each representing a tubing collar joint, and based on the number of collars that are counted and average joint length, which we get from the tally, we are able to calculate, we are able to determine the position and depth of the plunger at any given time. Right, so that helps us generate a velocity and depth profile against time. You can see it on the top right, on the bottom of that. So it's a bit small, but the straight line is basically your the depth profile, and the fluctuating line is your velocity profile, and on the x-axis is time. So we don't have time to go into much details in that bit. Once we have correlated depth correlated acoustic trace, then we proceed with the identification of key events. And these events include the operation of motor valves, which define the beginning and the end of the shut-in and flow cycle. And these are very easy to detect because they're marked by a very sharp change in wellhead pressure. This is followed by the plunger starting to fall in the tubing, and this is characterized by a slight but certain decrease in tubing pressure, which is because the weight of the tubing is now acting on the gas column beneath it in the tubing. So this is followed by then the plunger hitting liquid. When the plunger hits liquid, the tubing collar signals that we were using for depth correlation, they dilute, accompanied by a general, the amplitude of noise, it increases generally when the plunger is submerged in liquid. So eventually then the plunger hits bottom, the bumper springs only where it's rest, and the weight of the plunger is now transferred to the BSA, and we see an equal slight but certain rise in wellhead pressure, which we saw when the plunger started falling down. This is followed by the unloading period, which consists of the liquid arrival and plunger arrival. Those are also very easy to detect on the trace because they mark by a significant rise in both wellhead pressure and the acoustic noise. But if you happen to stand by the wellhead, you can even hear it happen. So we call it the surface events, and mostly these are annotated by the field teams themselves.